All right, let's jump right in. Welcome to this explainer. Today we're going to dive into the ultimate cheat sheet for literally every building block in existence. You've definitely seen the periodic table of elements hanging in a science classroom, and yeah, it looks a bit intimidating at first glance. But once you actually know how to read the map, it is an absolutely fascinating piece of human ingenuity.
So, what is the universe made of? It's kind of the ultimate question, right? If you were to zoom all the way in on the silicon inside your smartphone, or the oxygen you're breathing right now, or even the carbon in your own body, what's it all fundamentally made of? Well, the answer is surprisingly organized. Believe it or not, the vast, infinite complexity of the entire universe comes down to exactly 118 known elements. That is the whole shebang. From microscopic bacteria to a supermassive black hole, absolutely everything is built from different combinations of just 118 basic ingredients.
In this explainer, our agenda covers four main things: the ultimate cheat sheet, decoding the table's structure, the history of the table, and finally, exploring elemental groups.
Okay, Section 1, the ultimate cheat sheet, the master map of all elements.
Let's get our terms straight. An element is defined entirely by its atomic number, and that number is just how many positively charged protons are sitting right there in the nucleus of the atom. It's really that simple. Hydrogen has 1 proton, so its atomic number is 1. Carbon has 6 protons, so it's number 6. If you just add or subtract a single proton, you literally change the very nature of the substance.
Now, you might assume we just dug all these up out of the dirt, but actually, only elements 1 through 94 are naturally occurring on Earth. Elements 95 through 118, we had to make those ourselves. They're synthesized in advanced laboratories or nuclear reactors, and honestly, a lot of them exist for just fractions of a second before breaking apart. And when we look at the breakdown of those 118 elements, the composition is pretty wild. As you can tell, the vast majority, 93 of them to be exact, are metals. Then we've got 18 nonmetals, which includes things you're super familiar with like oxygen and nitrogen. And rounding it out, we have 7 metalloids sitting right in the middle.
Moving right along to Section 2, decoding the table's structure. Let's figure out how to read these coordinates.
So those horizontal rows going straight across the table, those are called periods. Every time you move one spot to the right, the element gains 1 proton. But here's the cool part. Every element in that same row has the exact same number of electron shells, kind of like layers of an onion. And as you travel across the period, the properties gradually shift from metal to nonmetal.
Then we have the vertical columns, which are called groups. Elements in the same group are essentially family members. Because they share the same number of outermost, or valence electrons, they behave and react in really similar ways. It's a total game changer for predicting how an element will act.
And that brings us to the periodic law, which states that chemical properties reoccur at regular intervals as the atomic number increases. This repeating pattern is the heartbeat of chemistry, and it's literally why we call it the periodic table.
On to Section 3, the history of the table. Let's look at the mastermind mapmakers who actually built this thing.
This wasn't an overnight discovery, it was like a giant puzzle spanning centuries. It kicks off around 1669 with Hennig Brandt discovering phosphorus. Then in 1789, Lavoisier starts grouping elements into basic categories. By 1864, Mayer is grouping them by valence. But the massive breakthrough happens in 1869 when Dmitri Mendeleev creates the periodic table we largely recognize today. Finally, in 1913, Moseley brings it all home by discovering the atomic number.
Now, Mendeleev is a legend for a very specific reason. He was so confident in the repeating patterns of his table that he intentionally left blank spaces. He literally predicted the existence of elements that hadn't even been discovered yet. But actually, scratch that. Mendeleev wasn't 100% perfect. His version ordered elements based on increasing atomic mass. Brilliant? Sure, but it led to a few weird inconsistencies. The modern periodic law fixed this by ordering elements based on increasing atomic number. Once Henry Moseley figured out that protons were the true key, everything clicked perfectly into place.
Finally, Section 4, exploring elemental groups. Let's meet the neighborhoods.
Let's look at a couple of these families side by side. Take Group 1, the alkali metals, which has 7 elements including lithium and sodium. Because of their structure, these guys are highly reactive. Drop pure sodium into water and it literally explodes. But then look way over at Group 18, the noble gases. also 7 elements, including helium and neon. They are so stable and unreactive that we use them to safely fill party balloons. Knowing the group tells you the element's whole personality.
And chemists take this grouping even further into 4 distinct subblocks: the S block, P block, D block, and F block. These are based on the specific shape of their valence electron orbitals. A great example is the D block, right in the middle of the table. That's where you find the classic heavy-duty transition metals we rely on every day, like iron, copper, and gold.
So, to wrap this all up, next time you're looking at this giant grid, remember these 3 steps. First, check the atomic number. Second, locate its period to see its electron shells. And third, find its group to understand its chemical traits. Suddenly, it's not a random jumble of letters. It's a fully functional map.
Which leaves us with a pretty thrilling question. Right now, our map stops at element 118. But considering everything from 95 onward was synthesized in a lab, what in the world is element 119 going to look like? And when are we going to find it? The universe is incredibly vast, and scientists are hunting for it. Right now, what wild properties will it have? Well, that's just a mystery waiting to be added to our ultimate cheat sheet. Thanks for joining me on this explainer, and keep looking closely at the building blocks of our world.